All right. So in this video, we're going to be looking at stoichiometry problems. All right. We're going to be looking at the relationships between different reaction quantities. Now, before you get started, you should have a calculator, periodic table, and probably some scratch work. All right. You need to pause these videos as I'm working these problems, work them on your own, and then see if you got them right. Okay. Now, from the overview video, overview PowerPoint, this slide is the most important slide that you'll have, okay? It tells you how to convert anything into anything else. So you need to know this slide like the back of your hand. We're probably going to look at it a couple times as you learn it, okay? So you need to be able to look at this slide. So let's start with just looking at a general equation. These are equations that have no elements whatsoever, just letters and symbols. So over here, we've got lowercase letters for our balanced coefficients, and the uppercase letters symbolize our elements or our compounds. In this case, as far as the reaction type itself, this would probably be like a double displacement reaction, okay? So the big takeaway here is that when you have a balanced equation, then you have a ratio of mole of A compared to mole of X. So I'll give you an example. Let's say these were the balanced numbers. All right. So now, what's the ratio of A to X? Well, it'd be 1 to 3. And if I know that, then I can put this into a bracket and convert from A into X. How can I do that? Well, remember when we converted something simple like grams? Let's say I have 1,000 grams, and I want to convert that to kilograms. We know that 1,000 grams is equal to 1 kilogram. Thus, in this case, 1,000 grams equals a kilogram. I've converted from unit A over to unit X. And in order to do that, I had to have a conversion, right? And the thing about a conversion factor, or that bracket, is that whatever's in that bracket has to be a true statement. It has to be valid. Well, if we go back to our numbers here, we say 1, 2, 3, 4. Well, then if I start with, we'll say 2 moles of A, and I want to know how many moles of X I can make, well, I know that 1 mole of A makes 3 moles of X. Thus, 2 times 3 is 6 moles of X. If I have a balanced equation, then I can convert from A to X. I can convert from anything in the equation to anything else in the equation, right? So that is huge. It's very important that you understand that. So let's look at one of those. Let's look at a Stoic problem. So given that there are 0.375 moles of oxygen, how many moles of water can be formed? All right. This is a mole to mole conversion. So we're going to write that down. Mole to mole conversion. As in moles of A to moles of X, right? 2 different moles. It takes one bracket to do a mole to mole conversion. Always. One bracket. So let's set it up. Our given is 0.375 moles of O2, of molecular oxygen, right there. All right. That means moles of O2 goes on the bottom. And because I have a balanced equation, I can compare the molar ratios of oxygen to water. So I can convert moles of O2 to moles of water. In this case, 1 mole of O2 yields 2 moles of water. Well, mole of O2 is on the top and on the bottom, so it divides out. We're left with moles of water. That's what the question asks us for. And in this case, we get 0.75 moles of H2O. There you go. There's a Stoic problem. One bracket, molar conversion. Okay, that's a mole to mole conversion. So to know moles in grams. So this is going to be, grams of X converted to moles of Y, right? It doesn't matter what variables we use, just grams of something converted to moles of something else. This is going to take two brackets, all right? And I just know that, right? And I'll show you how I know that in just a moment, but I know that. Grams to moles, two brackets. Moles to moles, one bracket, okay? So let's look for our given. We have 20 grams of hydrogen gas, so 20 grams of H2. That means that grams of H2 goes on the bottom because that's my given unit. Grams always goes to moles. And if I have grams of H2, I have to go to moles of H2. We know that 1 mole of H2 is 2 times 1.008. That's 2.016, right? That's from the periodic table. So this is a molar mass bracket, or a periodic table bracket. That gets rid of grams of H2, but I want moles of water. So I need another bracket. This is the only unit that I have right now, so it has to go to the bottom because I have to cancel it out. Well, can I go moles of H2 to moles of water? Yeah, absolutely, because I have a balanced equation. So moles of H2O, and now I'm just looking for the coefficients. So 2 moles of H2O is produced from 2 moles of H2. Mole cancels, and I'm left with my math problem. So 20 divided by 2.016 times 2 divided by 2. Well, just like moles of H2 on the bottom cancels out moles of H2 on top, a 2 on the top and the 2 on the bottom cancel. They go to 1. So really, I'm just doing 20 divided by 2.016, which in this case is 9.92 moles of H2O. All right, so how do I know this is a 2-bracket equation and that's a 1-bracket equation? Well, go back to the roadmap. If I'm going from moles of A to moles of B, I cross one bridge. If I cross one bridge, one arrow, that's one bracket. Every time I cross one of those arrows, there's a bracket. In the second one, we started with mass, right? We started with 20 grams of, what was it, H2, and we wanted to finish at moles of H2O, right here. So I had to go 1, 2 lines. I had to cross 2 bridges, so 2 brackets. And the next one we're going to go, let's look at it. So I have 100 grams of water. There's my given. I want to know how many grams of oxygen. That's where I'm trying to finish. So I'm starting with grams of X, and I'm finishing with grams of Y. So come back up here, right? We have 100 grams of water. That's where we're starting. And we want to know how many grams of oxygens, right? Mass. So I'm going to go 1, 2, 3 brackets. So before I even start, because I know this roadmap, I know I need 3 brackets to do this. Keeps me from getting stumped. So grams of water is going to go on the bottom. Anytime I have grams in the bracket, that's a periodic table bracket. It's a molar mass bracket because I have grams per mole. 1 mole of water is going to be equal to 2 hydrogens and an oxygen. That's 18.015 grams, 15.999 plus 2.016. That cancels out grams of water. I need a second bracket. Whatever's right here has to go on the bottom. So moles of water. Now, this middle bracket, this time it's going to be the middle bracket because remember I told you I know we're going to need 3. This is where I'm using my balanced equation to go from water, which is what I started with, right there's X, over here to oxygen, which is going to be my Z, my finishing thing. So moles of water to moles of O2. O2, right there, oxygen. Remember, oxygen is diatomic. When it's by itself, there's going to be 2 of them. And then, because the question asked me to go grams, so that cancels. Whatever's right here on top has to go on the bottom to cancel out. And we know we can go from moles to grams because that's what the periodic table lets us do. So 31.998 grams of oxygen, grams of O2, equals a mole of O2. 1 mole of O2 is equal to 2 moles of water in this equation. And so 100 divided by 18 divided by 2 times 31.998 leaves me with how much oxygen I make, which in this case is 88.81 grams of O2. This is a gram to gram conversion. It will always take 3 brackets to do that. I know that going in. It's just something that we can memorize. The brackets are always going to look like this. Periodic table, balanced equation, periodic table. Like that's where I'm going to get the information from. Another way you could think about it is molar mass, then molar ratio, and then another molar mass. Obviously, moles are important here. So 1, 2, 3. 1, 2, 3. So here's where I get my info, right? Info comes from here. Here's really what we're doing, and there is bracket 1, bracket 2, and bracket 3. Now, if we go back and look at the other brackets, we'll notice that we, like in the first one, in the second one, we did molar mass, then molar ratio. In the first one, we just did molar ratio, right? So we're using the same system over and over again, and just changing the numbers that we're putting into the brackets. Now, let's see where we can go with this, right? So these are pretty simple. I won't say they're simple. These are pretty basic stoichiometry problems. You either are going from moles to moles, or grams to moles, or grams to grams. That's pretty standard. Let's look at one that's a little bit more complicated. So this is called a Fermi problem, after Enrique Fermi, who would ask questions that were based on your best guess. Okay, so here's the question we want to answer. It says the average commute for American workers is 32 miles per day. The average fuel efficiency for American cars is 24.7 miles per gallon. I looked both of those things up for this problem. How many pounds of carbon dioxide are generated by the average daily commute of one worker? And right here, you probably recognize this as a combustion reaction because I have a hydrocarbon, right? So here's my fuel. This is octane. C8 is octane. Here is my oxygen. And we've made carbon dioxide and water, right? So because we know our types of reactions, we can recognize that there's our combustion reaction. So this is what our car is doing. So assuming that none of that carbon dioxide gets captured by, say, catalytic converter or some kind of emission control, how many pounds of carbon dioxide are generated by this average daily commute? Well, let's start with our given, okay? One worker is what we're looking at there. Hold on, let me grab my piece of paper here. So one worker, make sure I have all my numbers in front of me so we don't have to look up a bunch of stuff, right? That's what we're looking at here. So he goes 32 miles per one day. So there's my given. There's my per unit. Let's get rid of miles, all right? So I look up here in the problem and I see that I have 24.7 miles per gallon. That's useful. So 24.7 miles per 1 gallon. All right. And then we don't really use gallons a lot in science, right? We want to use the metric system. So I looked up 1 gallon is equal to 3.785 liters. Okay. I know that there is 1 liter has 1,000 milliliters in it. Keep going here. And 1 milliliter of gas, C8H18. I looked up the density to find this. Give me the grams, 0.7489 grams of C8H18. So let's talk about what I've done so far. So when we look at these other equations, we know that at some point to go from X to Y, or A to Z, whatever we want to call it, we have to go periodic table, balanced equation, periodic table. So I've taken what they gave me, 32 miles a day. Well, I got rid of miles and converted it to gallons. Got rid of gallons, converted it to liters, got rid of liters, converted it to milliliters, and used milliliters to get to grams, right? This is density, which we've talked about extensively this year. Now I have grams. Now I can do something with this, right? So there are, and again, I worked this out beforehand, 114.232 grams in 1 mole of our C8H18. There's our periodic table bracket. And according to our, right, so now that we have periodic table, we can do the molar ratio. So 2 moles of C8H18 can be converted into 16 moles of CO2. And now we got to get back, we want mass, right? We want pounds, so we got to get to grams, and then we can go from grams to pounds. So 1 mole, I'm going to run out of room, of CO2 is 44.011 grams. Right, and then we're going to start up down here. So there we go, right there. There's our bracket. So we need grams on bottom. So 1,000 grams is in 1 kilogram. And you probably know that 1 kilogram is 2.2 pounds. Now look at there. We took what we talked about with really simple stoichiometry, and we've taken it and applied it to something much bigger. So this should be 2.2. There we go. So when we run our math problem, this is pretty impressive. You make 24.9 pounds of CO2 per day. All right, let's make sure that worked out. So miles cancels, gallons cancels, liters cancels, milliliters cancels, grams of our gas cancels, moles of our gas, moles of our CO2, grams cancels, kilograms cancels, and I'm left with pounds on top and days on bottom. There we go. So the average American worker produces 24.9 pounds of CO2 per day. All right, let's take it a little further. Now let's add in some of our conversions. The average American worker works 260 days a year. So how many pounds of carbon dioxide are they responsible for annually, each worker? Well, this one's easy. 24.9 pounds of CO2 per day, right, per 1 day. And the average worker is going to work 260 days in 1 year. There we go. Days on top, days on bottom cancels. Now I'm going to have pounds per year. So that is 6,474.44 pounds of CO2 annually per year. That's a lot. That's like 3 tons and then a little bit more per person, right? So one more step. There's 115 million working Americans. So how much CO2, if they all have the average commute and they all drive an average car, do they produce? Well, we take our number from the last one, 6474.44 pounds of CO2 per year. And we're just going to multiply it over 1 by the number of workers, 115 million workers. Here's what that is equal to. 744,561,000,000 pounds per year. So that is hundreds, thousands, millions, billions, right? 744,561,000,000 pounds of CO2 enter the atmosphere from just our cars, just driving back and forth to work every year. That's a lot. That's a hard number to put into perspective. Let me show you what that would be in scientific notation, right? So we have 3, 6, 9, 10, 11. So that's 7.44 times 10 to the 11th pounds. Here's a good number to compare that to. There are 3 times 10 to the 11th stars in the Milky Way. That's what, roughly 2.5 times as much. So, yeah, if a star weighed a pound, right, we know it's obviously bigger than that, but just to kind of think about it, look up at night, each little star that you can see, it's half the stars, right, because the other half are in the southern hemisphere, 2.5 times that many stars, that's how many pounds of CO2 we put out of our cars driving to work. So stoichiometry can be used to tackle real-world problems with just a little bit of chemistry knowledge. All we needed to start with was this balanced equation right there, all right, and a good question. So that's some simple Stoic problems and then an advanced Stoic problem, all right? So if you have any questions, let me know.